5.2, evaluate and graph polynomial functions. So this comic is not directly related to this lesson at all, but in this chapter we will be talking about symmetry, about the origin, and here we just have a rotation about the origin, and it's kind of cute. So far in this course, we've dealt with linear functions, we've dealt with absolute value functions, and we've dealt with quadratic functions. And now we're going to go more generally into polynomial functions, and that just means that the degree here can be more than a first degree, which is linear, and a second degree, which is quadratic. And so we're going to deal with ones to the nth degree. And don't let this notation scare you. This is just saying that we have something times x to the n power plus something else times x to the n minus 1 power. So for example, you've already dealt with that when we were doing quadratics. We had something x squared plus something x. So you see this is x squared and this is x to the n minus 1 power here, and then we have just a constant, which we would say is our constant term there. This is our constant term there. And our leading coefficient in this case would just be the 5. And our degree in this case would just be a 2, a second degree. And it's important that when we write this, we put the highest degree out first. So here the squared is the highest degree we have, and the degree of our polynomial function is whatever the degree of our highest power is. When we say we have it in standard form, that's written in descending order of exponents, so that means that if we would have squared, we go squared, then just the x, then the constant. If we have cubed, then we would go cubed, squared, x, and then the constant. So highest power to smallest power. Again, the degree of our polynomial function is whatever our biggest exponent is. So just a little bit more explanation of the same thing I just said on that last side. If we have something of 0 degree, that just means, well, remember, x to the 0 power is just 1, so it's just a constant. And so an example would be like f of x equals a constant, 14, any number. A linear function is just f of x, or y equals something x. So y equals 5x minus 2 would be linear. A quadratic would be something with a squared in it. 5x squared plus 3x minus 2. A cubic would have a third degree in it. 5x cubed plus 4x squared plus 2x minus 8. I don't know. Doesn't matter what numbers you have in there. And then a quartic is just a fourth degree, so that means that the highest power is now the fourth degree. 16x to the fourth plus, let's just go with 5x cubed, plus 4x squared minus 8x plus 3. Now, if I have a fourth degree, that just means that the highest power is a 4. I don't have to fill in all these. I could actually have something like 16x to the fourth plus 8. That would also be a quartic. So I don't have to have actually like all of the exponents descending down. They could have zeros for some of them. Decide whether the function is a polynomial function. If so, write it in standard form and state its degree, type, and leading coefficient. So let's go for this. Now, x to the 1/2 power, x to the 1/2 power is the same thing as root x. I'm not sure if you've done that yet, but this would be 6 root x minus 5x. And so this would not be a polynomial function because I have a square root function, and that is not one of the types that we can have. In this example, though, where I have my root is just with a constant, and this is still 10 is a constant, but root 10 is also a constant. And so that's okay. See, I'm not doing anything to my x, and this is just my constant. So let's rewrite it in descending order, 5th, and then the 4th power, and then the squared power, and then the constant is always last. And so this is a polynomial function, We just wrote it in standard form here. I'm just going to abbreviate it SF. The degree is just 5. It's the biggest degree I see. The type is just a 5th degree, and when we say beyond a quartic, we don't name it anything, just the 5th degree, so I don't even need the type here. And then the leading coefficient, I'm going to call that LC. The leading coefficient is just what's in front of that highest power, and that would be a -8. All right, this next one, yeah, that's a cubic actually, so yes. And it's already in standard form because I have them from highest power to smallest. And then let's see, the type we would say is cubic. And the leading coefficient is just what's in front of that x cubed. Well, there's nothing there, so it's just a 1. Now let's look at this one. Oh, well, I have a negative exponent. I cannot have negative exponents, so no, this is not a polynomial function. Let's use direct substitution to evaluate this function when x equals 2. So that means I'm just trying to evaluate f of 2. And so that means wherever I have an x, I'm going to substitute in a 2. -3, 2 cubed plus 2 squared minus 12 times 2 minus 5. And so we get -3 times 2 cubed is 8. Plus 4 minus 24 minus 5. Let's see, -24 plus 4 is -20. Minus 24 minus 5 is -49. And so that would be my final answer. Okay, this one, I actually already solved this for you because we just did it in the last one. So to evaluate f of 3, the first method I could use is direct substitution, which is what I just did in the last example, and just put a 3 in everywhere I see an x. Okay, and then I solve that. Another method is to use synthetic substitution, and this is something new that we haven't done. And in this case, I'm just going to tell you that direct substitution is much easier, but we're going to use synthetic substitution, synthetic division in the future, and so I want you to know it for an easy example here. So what I do is, I first just write out all of my coefficients. So the first step is to write out all the coefficients. So I have a 2 is my 4th degree. And then I have my cube degree, then I would have my squared, then I would just have my x, and then I'm going to have my constant. Okay, so I'm just going to write this as my heading. It's not actually part of my problem. All right, so I have a 2, then I have a -5 as a coefficient. Now I have no squared term, so I need to put a 0 as my placeholder. Now, in front of the x, I have a -4 as a coefficient, and my constant's just the 8. And then my x value is just going to be the 3. That's what I want to evaluate. And so I leave some space here because I'm going to write something in there, okay? And then what I do is the first step is you just bring down this 2, okay? And then you multiply. So 3 times 2 is 6. And then I add. So -5 plus 6 is 1. Then I do the same thing. 1 times 3 is 3, and then I add 3. 3 times 3 is 9. 9 minus 4 is 5. Multiply again is 15, and then you add 23. And so my answer is just this part right here. And so that means that f of 3 is 23. All right, so if I wanted to do f of 5, for instance, I would have put a 5 out here. All right, and whatever is this last thing is my final answer. Now, why we do this and what this all means, we're going to talk more about later. So just keep this in the back of your mind, and this is called synthetic substitution. Let's go ahead and use synthetic substitution to evaluate this one. So I'm going to just write my little placeholders up here, squared, then I'm going to have my x term, and then I'm going to have my constant. And I have my x value right out here. Okay, So my x value is just 2, and I have negative 3 as the coefficient, 1, negative 12, and then negative 5 is my constant term. Leave some space, bring this one down, negative 3, multiply, negative 6, then you add, negative 5. Negative 5 times 2 is negative 10. Then you add, negative 22. Multiply. Negative 22 times 2 is negative 44. Then you add, negative 49. And so my answer, f of 2, is negative 49. Finally, let's talk about the end behavior of polynomial functions. So this is actually very important. If my degree is odd, meaning if it's linear, if it's a cubic, if it's a fifth degree, anything with an odd degree, and the leading coefficient is positive, then when I'm looking at my end behavior, okay, this says as x goes to positive infinity. That means as x goes all the way off to positive infinity, as my x value gets huge, what's happening to y? As x gets huge, what happens to y? That's what this is saying, okay? That's how I say it in English. And so you'll see that y gets huge in this example, right? So y is also getting huge. Now here this is saying as x goes to negative infinity. That's saying as x gets tiny, what happens to y? That's what this is saying in plain English. And so as I go over to tiny values of x, I get tiny values of y. See that? Now let's look at this one. As I look at tiny values of x, I actually get huge values of y. Huge values of y. Positive infinity is big. Negative infinity is small. Now let's look at this other side. As x gets huge, what's happening to y? It's getting teeny tiny. Teeny tiny. All right, and this happens when my degree again is odd, but my leading coefficient now is going to be negative. Now, honestly, I drew these pictures here, but when I think about this, I think about my most simple case, and my most simple case is just a line. Let me just draw some axes for both of these. And so now, if the leading coefficient is positive, positive would mean that the slope is positive. So if my slope is positive, you'll see that all these properties hold true. As my x gets huge, my y gets huge. As my x gets tiny, my y gets tiny. Now, if the leading coefficient's negative, or if I have a negative slope, as my x gets tiny, my y gets huge. As my x gets huge, my y gets tiny. And so all these properties hold true. Now let's go to the next ones, which are going to just be even degree. And so I accidentally wrote in that space. This is even degree. And the leading coefficient here, let's start with positive. And then we're going to do an even degree, and the leading coefficient is going to be negative here. So what happens? Let's see. As x is huge, as x gets huge, what happens to y here? Y also gets huge. But as x gets tiny, y, in this case, is also getting huge. So as x gets tiny, y is also getting huge. So you'll see that I actually have the same thing happening on the right and the left when it's even versus when it's odd. I have opposite stuff going on. Okay, so now let's see. As x gets teeny tiny, if I have a negative leading coefficient, then it goes teeny tiny y. As x gets huge, I get a teeny tiny y also. So you'll see that it's very different if I have odd or even. And now again, I want to go back to my simplest case. Let me just draw an axis over here and an axis over here for my simplest case scenario. So my simplest case would just be a quadratic, the second degree, the parabola that we've been dealing with in the last lesson. And so if it is positive, that means, remember, it opens up. And if it's negative, remember, that means it's opening down. And you'll see that the behaviors hold true. I go to positive infinity for both the y's, and I go to negative infinity for both the y's in this one. So again, I would always just think about my simplest case when I'm trying to figure these out. And most importantly, the end behavior is determined by the function's degree and leading coefficient. So whenever I'm asking you these types of questions, you are going to be looking at the degree and the leading coefficient to determine all your answers. You don't have to do anything more than that. So let's go ahead and look at this problem. Well, we know since one side's opening down and the other side's opening up, we know that the degree is going to be odd. And what do I know about the leading coefficient? Well, let's think about it. Let's make our line look like this. If we had a line that looked kind of like this, it would be going like that, right? If I wanted it to start down and end up. And so does that have a positive slope or a negative slope? Positive. And so that's how I remember that the leading coefficient is positive. And that's all I need to do. Again, because one side was one way and the other side was the other way, I know that it's odd. And if I just draw the simplest case, which is my line through it, then it's a positive slope, so the leading coefficient is positive. And I know this is not on your PowerPoint because I'm just making up right now, but I just realized I didn't do an even one, so let me just draw one like this, and let's try this problem. Well, again, in this one, since the same thing is happening on both sides, the degree is going to be even. And let's just think about our simplest case so we can figure out that leading coefficient. So our simplest case would be like a quadratic that looked like that. And so since it's opening down, I know that it's going to be negative. And so that's all I do for that. Again, think about your simplest case. Now let's go ahead and try and graph these. What I care most about is that we're getting this degree leading coefficient and able to fill out this chart. Otherwise, we're just plotting points, which you all know how to do. The degree of this is just cubic. It's already in descending order. And the leading coefficient is -1. So it is negative. The degree is odd. And the leading coefficient's negative. So if you were thinking about a line with a downward slope, that means I'm going to start up here and I'm going to end down here. That's what all this means. So I can already fill out this part. As my x gets, let's just start with, as x gets huge, doesn't matter which way you start. As x gets huge, what's happening to y? It's getting tiny. As x gets small, what's happening to y? It's getting huge. Okay, so now let's plot some points and hope that it works. So why don't we start with f of 0? So put in 0. 0, 0, 0, -3. 1, 2, 3. Now let's just put in a 1. So -1 plus 1 is 0, plus 3 is 3, minus 3 is 0. So I have the point 1, 0. Let's put in another point 2. If I put in a 2, I get out a -1. And let's put in a -1. I would get out a -4. 1, 2, 3, 4. And if I put in a -2, I would get out a 3. So I'm just plotting points. Okay, and if you actually looked at that, you could look it on your calculator. You'll see that we did not pick up all the important points here at all, because it actually goes down a bit more and it actually goes up a bit more after this. So I just plotted on my calculator to get the sketch. Again, I could care less about the sketch at this moment in time because I'm really just doing that on my calculator for right now. What I care about in this problem is that you can fill in all of this information here. So now we have an even degree. The degree is 4, which is even, and the leading coefficient is 1, which is positive. Okay, and again, first step, make sure that they're in descending order, which they already are in this case. So even positive would be like my normal parabola opening up here and here. So as x gets huge and as x gets tiny, my y is always going to be huge, no matter what happens to x. Okay? And so now, again, I'm just going to plot points in this one. If I put in a 0, I should get out a 4. 1, 2, 3, 4. If I put in a 1, I would get out a 0. If I put in a 2, I get out a 4. 1, 2, sorry, negative 4. If I put in a negative 1, I get out a 2. And if I put in a negative 2, I get out a 12, which is big. So, again, I'm doing this one on my calculator. And it looks something like this. Again, I don't care that much about the sketching right now because there's a whole lot more that we've got to learn. What I care about is all of this stuff.
And that's it for this lesson.
Bye.